Now continuing with the application of electrolysis, already one application we have seen it, that is electroplating, we have seen it. Remember it, for the articles to be electroplated should be made the cathode, and the which you are going to electroplate it, that should be made the anode, but it should be pure, free from any impurities, grease, whatever it is. And the electrolyte should contain the ions, same as that of the anode, we can say that. Clear? That you must remember it. These are a few things. Now next is electro refining. Now basically there are many metals are there which we need to refine it after the extraction. Many metals, most of the metals, except the active metals, we can say that. That is, you need to refine it after the extraction, so as to get pure metal, we can say that. So what is electro refining? It is a term, it is used, it is a process, it is a term which is used in which the metals containing impurities are purified electrolytically. The metals which contains impurities, it is being removed electrolytically, so that the purity is nearly 99.9%, almost 100%, we can say that, the purities. Alright, that is called electro refining of metals. So which metals basically is being done? Basically we go for what you can say zinc, we go for copper, we go for lead, got it? So we go for silver. In this way we go for electro refining of all these metals. Clear? Zinc is there, copper is there, silver is there, lead is there, nickel is there, we can say that. Clear? We go for electro refining of all these metals after their extraction. When we extract it, you will be studying about the extraction of metals in metallurgy chapter. After their extraction, we go for the electro refining. Alright. Now, when we go for electro refining, what you need to do? Here also same thing. You will take an electrolytic tank. Alright, an electrolytic tank you will be taking it. For example, here we see the electro refining of copper. Now, the pure copper will be made the cathode. Here, the pure copper will be made the cathode, and the impure copper is your anode. The impure copper is the anode. Alright, so this is your impure copper and this is your pure copper, which will make us the cathode. Not clear? So you can see it. This is your cathode, negative terminal, and positive terminal, the battery is your anode. Now next is that is what you need to do. That is, you will be taking a copper sulfate solution as an electrolyte. If you are doing the copper refining, you will take copper sulfate solution as electrolyte, we can say that, CuSO4 solution as an electrolyte, you will take it, fine. Now next thing, one thing here you have to remember it, that the impure copper should be what you can say thicker, and it should be thinner, because this the pure copper ions will go and deposit here. So at the end of the reaction you will see this becomes thicker and this becomes thinner. So time to time you need to replace the anode. Time to time. In the electroplating also the same thing. You need to replace the anode time to time, because the anode is used up, isn't it? The anode is used up. So hence, as the anode is getting used up, so it is thicker, and as it is getting used up, it becomes thinner. And when it becomes thinner, means the resistance increases. And resistance, if it will increase, less current will flow through it. You have studied in physics, in Ohm's law, you might have studied this. The resistance is inversely proportional to the cross-sectional area. If the cross-sectional area is less, the resistance will be more. If the cross-sectional area is more, the resistance will be less. And if resistance is less, current will be more. Isn't it? Yeah. So in this way, what you find is that here, impure copper, I have taken it. Let me write here. I don't have much space. This is your impure copper. Fine. So now, copper sulfate solution I have taken it. CuSO4 will dissociate to give you Cu2 plus and SO4 2 minus, we can say. Solution means water, which will dissociate to give you H plus and OH minus. Fine. H plus and OH minus, you are getting it. Okay, fine. Now, what I said here, add cathode. So, add cathode, which will go, nothing but copper is going to go, because copper and H plus ion, if you compare, copper is below H plus ion in the electrochemical series. So, Cu2 plus plus 2E minus will give you Cu. So, copper gets deposited at the cathode. Fine. Add anode, as it is again active electrode. So Cu minus 2E minus will give you Cu2 plus. So whatever the copper ions is there, the pure copper ions, it goes to the electrolyte, and from the electrolyte it gets deposited at the cathode. Just now I said you. Now what you will find is that here when the reaction will start, after the reaction has started, the reaction is continuing, you will find it here, that is a deposition, you will get it below the anode, you will get a deposition here, or that at the bottom of the tank also you can say that a deposition will be there. Alright, why? What is this? They are nothing but impurities which are present in copper, it gets settles down. Impurities here, in case of copper, the impurities present are silver, gold, costly material, we can say that, costly metal, platinum, you will be getting it, the impurities. And this is known as anode mud or slime, we can say that. This is the impurities which are settling at the bottom of the tank is nothing but known as the anode mud or slime. The impurities which are present in the anode, that gets settles there, and it is very costly. That is very costly, because what I said, it contains, like in case of copper, it contains gold, silver, platinum. These metals generally are present in anode mud or slime. In this way, we go for electro refining of nothing but copper. So remember that in case of refining, the the material which is to be refined, the metal which is to be refined, that is kept as the anode, the impure one, and the pure one should be kept at the cathode. And the electrolyte should be of the same solution. If it is copper, then copper sulfate. If it is nickel, then nickel sulfate solution. If it is silver, then silver cyanide solution, or sodium argento cyanide solution. In the previous case, we have taken it. Alright, fine. Now, next. After that, the last one is your electrometallurgy. Now, about electrometallurgy, you will study more in your metallurgy chapter. So, electrometallurgy, I said you, electroplating, electrorefining, and electrometallurgy. So, electrometallurgy is a process of extraction of metals by the help of electrolysis. This is known as electrometallurgy. The process of extraction of metals by the help of electrolysis. Now, here the question comes, why do we need to extract the metals by the help of electrolysis? Why do we need? First of all, which metals are to be electrolyzed? That is sodium, potassium, calcium, magnesium, aluminium. So basically, you will find the metals which are higher in the metal activity series. So they are highly reactive in nature. So hence they cannot be reduced. If you go for, instead of going for electrometallurgy, if you are going for ordinary reduction process. Got it? Ordinary reduction process. Ordinary reduction means reduction by the help of carbon, that's coke, carbon monoxide or hydrogen, because these are the basic reducing agent which we use to reduce metallic oxide to metals. Metallic oxide to metal. These are the basic reducing agent we use it. That is coke, carbon monoxide, hydrogen. So it cannot be reduced. Coke, carbon monoxide and hydrogen cannot be used for the reduction of this, this metallic oxide to metals. It cannot be used because they are highly reactive in nature. So hence this ordinary reducing agent cannot reduce its oxide to its respective metal. Listen carefully. The ordinary reducing agent cannot reduce the oxide of its metals, of these metals, to its, to respective metals, we can say that. It cannot reduce because they are highly reactive in nature. First point. Second point is that these metals have got strong affinity for oxygen. Let us say that you have reduced it also by the help of this reducing agent. Immediately again it will react with oxygen to form respective oxide. For example, you know that aluminium has got strong affinity for oxygen. Strong affinity for oxygen. It forms alumina, Al2O3. Got it? Strong affinity for oxygen. So hence it cannot be reduced by ordinary reducing agent. Because if it at all it is reduced also, let us say it is reduced, it will immediately combine with oxygen again to form again alumina, Al2O3. Again oxide it will be formed. Then what is the use of reducing that metals by using the reducing agent? So it cannot be done. Got it? Now next is, as I said, their oxides are highly stable. So hence it cannot be reduced. They are highly stable. They are oxides. Sodium oxide, potassium oxide, calcium oxide. They are highly stable in nature. Got it? It cannot be reduced by reducing agent, neither by heating also. You will say, sir, we'll heat it strongly. No, it can't be done. Because what I said, highly stable in nature. They are quite stable. Got it? So only it can be done by the help of electrolysis. Only it can be done. So these metals generally we extract it by the help of electrometallurgy. These metals. Got it? I think you got the reason. That why do we need to go for electrometallurgy of these metals, we can say that. Clear? So next is that when you are going for the electrometallurgy of these metals, remember one more thing. That is, don't take the aqueous solution of this salt. Don't take. For example, if you want to extract sodium, you will be extracting sodium by sodium chloride, molten sodium chloride or fused sodium chloride, not by sodium chloride solution. Why? Because solution means Na plus and H plus ion will be there. You know that according to electrochemical series, if both the ions are present, which will go to the cathode? H plus ion. So if H plus ion goes to the cathode, what you will be getting from the cathode? Hydrogen gas will be liberated. But do you want that hydrogen gas to be liberated? Are you doing electrometallurgy of hydrogen gas? No, metals. So hence here you should not take, because all these metals which I wrote, potassium, sodium, calcium, magnesium, aluminium, if you take their aqueous solution, then H plus ions will be there, and H plus ion is lower in the electrochemical series. And I said you last class also that the ions which are placed at the bottom of the electrochemical series gets the first preference to get deposited at the respective electrode. So hence potassium, sodium, calcium will not get. So hence you are not supposed to take the aqueous solution of this salt for electrolysis of these metals, for electrometallurgy of these metals. What you are supposed to take? You are supposed to take the fused salt, molten state. For example, you should take here sodium chloride molten, NaCl, in the molten state you will take it, or the fused state. It will give you Na plus Cl minus. So at cathode, one cation and one anion is there, so Na plus E minus will give you what? Na. So sodium is deposited at cathode, you can see. And at anode, what you will be getting? At anode, there is no choice for you. Cl minus E minus will give you Cl. Cl plus Cl will give you Cl2. So chlorine gas is liberated. I am not interested, I am interested with sodium. So sodium is getting collected at the cathode. Similarly, if you want to extract potassium, then you need to take potassium chloride in the molten state. Got it? So in this way, in case of electrometallurgy, the electrolyte should be in the molten state, not in the aqueous solution state of the active metals which you are taking it. And I've said you why active metals only can be extracted by the help of electrometallurgy. They cannot be extracted by taking ordinary reducing agent. Okay? This is all about your chapter. Thank you very much.